Welcome to section 2.4, Applications. Now that we've learned how to solve right triangles, it's time. It's time to apply these skills to practical scenarios. So trigonometric plays a crucial role in solving real-world problems involving angles, distances, heights, and navigation. In this section, we will use our knowledge of right triangle relationships to analyze and solve application-based problems, which reinforce the importance of trigonometry beyond the classroom. So we have three objectives in this section. The first one, solve application problems involving right triangles. Right triangles are widely used in real-world applications, from construction to physics. By applying trigonometric ratios such as sine, cosine, and tangent, we can determine unknown side lengths and angles in various problem scenarios. Understanding how to set up and solve these problems is essential for practical applications of trigonometry. First example, the two equal sides of an isosceles triangle are each 14 centimeters. If each of the equal angles measure 48 degrees, find the lengths of the base and the length of the altitude. So we know we're working with an isosceles triangle. An isosceles triangle has a base, two sides that are congruent to each other, and a height that's perpendicular to the base. So we know that the two equal sides are 14 centimeters, and we know each of the equal angles are 48. So this is 48, and this is 48. We want to find the length of the base and the length of the altitude, so that would be the height. So we want to find the height and the base. Okay. Well, as you see here, we have two triangles within this one triangle. So to find our unknowns, we can use just half of our whole triangle to find our unknowns and then adjust accordingly. So let's just use this left side here, this left side triangle right here. Okay, we know that the whole base here is y. But just for the purposes of this triangle, we are going to make this base of our half of our isosceles triangle y. And then we'll apply it to the big Y at the end. Okay? All right. So to solve our problem, we know the angle, which is 48 degrees. We know the hypotenuse. So if we were to use one of our trig functions, we could use sine to help us because we know the opposite, or we're trying to find the opposite side, but we know the hypotenuse. So the sine of 48 degrees equals x over 14. So opposite over hypotenuse. So to find x, we would take 14 times the sine of 48 degrees. When we plug this into our calculator, rounding to two significant figures, we would have 10 centimeters. Since x is the altitude, we know the altitude is 10 centimeters. Okay? So now we know x. So now we can find our y using, again, this triangle to the left. So to find y, we know our angle, we know y is adjacent to that angle, and we know our hypotenuse. So now we would be using cosine of 48 degrees equals y over 14. So y will equal 14 times the cosine of 48. So y equals 9.3678284 when you enter that into your calculator. But since this y represents only part of the big Y, we now need to multiply y by 2. So we're not rounding yet. We're not rounding yet. All right, we round at the very end. So we're going to take our y and multiply it by 2 and round that value to two significant values. So that would get us 19 centimeters. So our base of the whole isosceles triangle is 19 centimeters. Okay, great. All right, objective number 2, so B. Solve problems involving angles of elevation and depression. Angles of elevation and depression help us measure heights and distances when direct measurement is not possible. These angles are commonly used in fields like engineering, architecture, and aviation to calculate the height of objects or the distance between points using trigonometry. An angle measured from the horizontal up is called an angle of elevation or inclination. An angle measured from the horizontal down is called an angle of depression. All right, and you see here in figure 2, in our first angle, we have our horizontal, and when we move up, we have an angle of elevation, whereas in the second image from our horizontal, if we are moving down, we have an angle of depression. And these angles of elevation and depression are always considered positive angles. Okay. So in our second example here, if a 65-foot flagpole casts a shadow of 37 feet long to the nearest 10 minutes, what is the angle of elevation of the sun from the tip of the shadow? So let's draw an image to help us. So we have a flagpole. So let's draw our flagpole here. Okay, and then our flag. All right, and our flagpole casts a shadow. Okay, so it's going to cast a shadow. All right. Okay. And our flagpole is 65 feet. Our shadow is 37 feet. To the nearest 10 minutes, so we'll just need to make sure that we round to the nearest 10 minutes. What is the elevation of the sun from the tip of the shadow? So the sun would be up here. Okay. So we want the angle of elevation. So that's what this would be. The angle of elevation. From the horizontal up. Okay. So we want the angle of elevation. So we can give this theta. We want theta. So knowing our trig functions, SOHCAHTOA, we know our angle is theta, it's unknown. From theta's point of view, we know the opposite and we know the adjacent. So that means we'll be using tangent to help us find theta. So the tan of theta is the opposite, 65, over the adjacent, 37. So to find theta, we'll take the inverse of tan, which is 65 over 37, of 65 over 37, and we'll get 60.350136 in our calculator, rounding to two significant digits. We will get theta, looks like a halo. Let's rewrite that one. Theta equals 60 degrees. Okay. But now, since it tells us to round to the nearest 10 minutes, we want to convert the decimal part of our of our decimal to minutes. And why do we do this? Well, the reason we convert the decimal part of the degree measurement into minutes is that angles are often expressed in degrees, minutes, and seconds. So it's called the DMS format instead of decimal degrees. This is commonly used in navigation, surveying, and even trig problems like the one that we're doing now. So why convert decimals to minutes? Well, one, you need to understand angle units. So 1 degree is going to be equal to 60 minutes, and 1 minute is equal to 60 seconds. The whole number part is the part that represents the degree, and then the decimal part represents a fraction of a degree, which we can convert into minutes just by multiplying by 60, since there are 60 minutes in a degree. Okay, so we'll take our decimal part, 0.350136, and we'll multiply it by 60, and we'll get roughly 21.008189 but it asks us to round to the nearest 10 minutes. So this is 21.008189 to the nearest 10 would be 20 minutes. Okay. So that means our angle of elevation is 60 degrees and 20 minutes. Okay. Alrighty. Let's box our answer. Okay. So number 3, exercise 3. A man climbs 235 meters up the side of a pyramid and finds that the angle of depression to his starting point is 56.2 degrees. How high off the ground is he? Okay, so we're dealing with the side of a pyramid. So that is going to be a triangle. Okay. And he climbs up 235 meters. So this is going to be 235 meters. And he finds that the angle of depression to his starting point. Okay, so the angle of depression to his starting point. So when he reaches the top, all the way down is 56.2. Okay, so that means this angle measurement right here is 56.2 degrees. Let's move this 230 down just so that we can see it a little better. 235. Okay. How high is he off the ground? Okay, so we want to know how high he is off the ground. So we want to know x. Okay, so to redraw this triangle that I just created, it's a right triangle. Okay, we know this is 235. That is our hypotenuse. And we know this angle is 56.2 degrees. And we want to find x. So if we're looking from the perspective of our angle here, we have our hypotenuse and we have the side across or opposite our angle. So opposite over hypotenuse would be sine. So we want the sine of 56.2 degrees, which is opposite over hypotenuse. So x would equal 235 times the sine of 56.2 degrees. So when we enter that in our calculator, we'll get 195.2813503. Our values in our problem are represented as 3 significant digits. So we are going to give our answer in 3 significant digits, which would be 195, adding our units, meters. So the man is 195 meters off the ground. All right. Number 4. Figure 5 is a diagram that shows how Diane estimates the height h of a flagpole. She can't measure the distance between herself and the flagpole directly because there's a fence in the way. If Diane finds the angle of elevation at point A to be 57.6, so that's this right here, 57.6 degrees, she then turns 90 degrees and walks 30 feet to point B. Okay, so this is 30 feet. And measures the angle between her path and the base of the pole to be 49.2 degrees. Find the height of the flagpole. Okay, so I've labeled everything that I know according to the problem that was given to me. So I have a fence, I have a flagpole on the opposite side of the fence. Diane is on the other side. We are trying to find the height of the flagpole. I know the angle of elevation when she's at point A is 57.6 degrees. When she turns 90 degrees and walks to B, her angle measure is now 49.2 degrees between her path and the base of the pole. So, as you see in this image, we have 2 different triangles, okay? And we're going to use these triangles to help us find h. So the first thing that we're going to do is we are going to find x. We're going to find x of our flat triangle here at the bottom. Right, so this triangle here at the bottom where we have a 90-degree angle. We know this is 49.2. We know the base here is 30, and we're trying to find x. Okay. Once we found x, then we can find h, because x is also the base of our second triangle, where our angle measure here is 57.6 degrees. We're trying to find H, and the bottom here is X. So once we find X, then we're able to find H. So let's find X. So to find X, we know from our point of view, for our angle 49.2, X is opposite, and we have an adjacent side. So we can use the tan of 49.2 equals X over 30. So X will equal 30 times the tangent of 49.2. This will get us 34.755333451. Now we can't round because we need this value for the next step in order to find H. So now that we know what X equals, we can find H. So from the point of view of our angle 57.6, we're trying to find H, which is opposite our angle, and we know the adjacent. We know X, all right, because X is the 34.755333451. So we're going to take the tangent of 57.6 equals H over X. So H will equal X times the tan of 57.6. All right. And so then we'll take H times 34.755333451 times the tan of 57.6. So H will equal 54.76564,398. So H, rounded to 3 significant digits, will be 54.8 feet. So the height of our flagpole is 54.8 feet. Alrighty. Exercise number 5. Figure 6 shows the topograph map of Bishop Peak in San Luis Obispo, California. I'm probably pronouncing that wrong. Suppose Stacy and Amy are climbing Bishop's Peak. Stacy is at position S and Amy is at position A. Find the angle of elevation from Amy to Stacy. So this is an image of a topograph map, meaning that the curves that you see here are different levels of elevation. Okay. Now, Amy is at position A and Stacy is at position S. We also know on this graph that our contour intervals equal 40 feet. So all of these squiggly lines represents a distance of 40 feet between the next contour. Okay, so between Amy and Stacy, if we were to count, we would have 1, 2, 3 contour intervals between them, meaning that there's 120 feet between Amy and Stacy. Okay, what else do we know? Well, we know, since this is a map, that if we were to measure the distance between Amy and Stacy using a ruler, we could then convert it to feet to determine the actual distance between Amy and Stacy. So 1 inch on this map is going to represent 1,600 feet. All right. So we are asked to find the angle of elevation between Amy and Stacy. Well, to help us out, I have measured between Amy and Stacy, and I found that the measurement between Amy and Stacy is 3/8 of an inch. Okay, 3/8 of an inch. So, since I know the distance between them is 3/8 of an inch, I can find their actual distance between them. So I'm going to take 3/8 of an inch and I'm going to multiply it by 1,600. Okay. Why am I going to do that? Well, I know that for every 1,600 feet, I have 1 inch on my map. The inches measurements cancel, leaving me with just feet. So when I multiply, I'll get 600 feet. So I know that the horizontal distance between Amy and Stacy is 600 feet. Okay. So now we need to find the vertical distance. Okay. So I know the horizontal from this map, but I now need to find the actual vertical distance between them. Well, the number of contour intervals between them, remember, was 3. So the elevation is going to change between them by 40 feet, according to my map. So since there are 3 contour intervals, and between each contour interval is 40 feet, I'm going to multiply 40 times 3, and I'll get 120 feet. So I know the horizontal distance, and I now know the vertical distance. Okay? And so now I can use this information to help me find my angle of elevation. So I'm going to draw our triangle here. I know Stacy is higher than Amy. Okay. I know my horizontal distance is 600, and I know my vertical distance is 120. Okay. I want to find my angle of elevation from Amy to Stacy. So I'm trying to find angle A. So from the perspective of angle A, I have an opposite side and an adjacent side. So I'm going to use the tan of A to find my theta. Okay, so the opposite is 120 over the adjacent, which is 600. To find the measurement of angle A, I'm going to take the inverse of tan. Okay, and I'm going to plug this into my calculator, rounding to 3 significant digits, and I'll get A equals 11.3 degrees. So Amy must look up at an angle of 11.3 degrees from straight ahead to see Stacy. Awesome. Now you know how to read a map and find calculations. Isn't this so cool? All right, so number 6. The support wires for a cell phone tower are anchored to the ground at an angle of 62 degrees. If the cell phone tower is 120 feet tall, find the distance from the anchor point to the base of the tower. So we have a cell phone tower, and they're like something like this, I think. Let's just say this is a cell phone tower. Okay. And the support wire is anchored to the ground at an angle of 62 degrees. So the support wire is anchored to the ground. We're just going to pretend this right here is a straight line. Okay. At 62 degrees. It's anchored to the ground. And the cell phone tower is 120 feet tall. Okay, so this is 120 feet. Find the distance from the anchor to the base of the tower. So we're trying to find the base, x. So from the perspective of our angle 62, we have an opposite side and we want to find an adjacent side. So we will be using tangent to help us find that. So opposite over adjacent. Okay. So we will multiply both sides by x, which will eliminate x from the denominator, and then divide both sides by the tan of 62. Plug this value into our calculator. We will get a long decimal. Then we need to round to 3 significant digits. So we'll get 63.8 feet as the distance from the anchor to the base of the tower. That was fun. Don't you just love drawing images and then figuring out? It's like a mystery. Anyway, let's continue. All right, exercise 7. A man standing on the street looks up to the top of a building and finds the angle of elevation is 52 degrees. He then walks 25 feet further away and measures the angle of elevation to be 47 degrees. How tall is the building? Okay, let's draw our image. We have a man standing on the street and he looks up at a building. Okay, so let's draw a building. Okay, that's our building. And we have a man on the street and he looks up at the building. Okay, so let's just say that he looks up at the building. This is our man. And he looks up at the building and he finds his angle of elevation is 52. So this is 52 degrees. He then walks 15 feet further away. Or sorry, not 15, 25 feet further away. Okay. So he walks another 25 feet further away. And he finds that angle of elevation to be 47 degrees. Okay. How tall is the building? Oh, so we want to find this height, the height of this building. Okay. All right. Well, we know a couple things. We know the distance that he walked between, I guess you could say, point A and point B is 25 feet. We don't know the distance between the building and where he first looked up to the top of the building. We don't know that. And we know the 2 angle measures of elevation. Okay. So let's first set up how we would solve for h. Okay. So in our first triangle, well, that would be this one. First part, this one right here. This is our first triangle. To find h, I would need to use the tangent, opposite over adjacent. So tan of 52 would equal h over x. Okay, that's the first triangle. The second triangle, here in green, okay, I now have a base that is 25 plus x. So my tan of 47 would be h over 25 plus x. Okay. So these would be the processes that I would take to find h. Now, both of them have an h. So let's rearrange both of these in terms of h. So the first one, h would equal x times the tan of 52 degrees. And the next one, h would equal 25 plus x times the tan of 47 degrees. Okay? So I have h equaling x times tan of 52 degrees and h equaling 25 plus x times the tan of 47 degrees. Both of these expressions equal h. Well, since I know h equals h, I can set both of these expressions equal to each other. So the x times the tan of 52 equals 25 plus x times the tan of 47. And now I can use algebra to help me find x. So I'm going to distribute the tan of 47 on the left-hand side to each term. And did I say left-hand side? I meant right-hand side. Then the left-hand side stays the same. I now will subtract the terms that have x to one side. So I'll have x times the tan of 52 minus x times the tan of 47 equals 25 tan of 47. Now on the left-hand side, both terms have x, so I'm going to factor out an x. Remember, the goal is to get x by itself. The right-hand side stays the same. Now to get x by itself, I'm now going to divide both sides by tan of 52 minus the tan of 47. This whole ratio I'm going to enter into my calculator, and I'll get 129.15566. So I now know what x equals. Okay? But remember, I'm not done yet. I'm trying to find the height. Okay? So now that I know what x equals, I can use either original function up here at the top to help me find what h equals. I'm going to use the red equation to help me find h. Okay, so I know h equals x times the tan of 52. So I'm going to take my x and I'm going to multiply it by the tan of 52. Okay, and I'm going to get 165.3117063. Since my values in my problem are rounded to two significant figures, all right, and my value here has a whole number and a decimal part, I'm going to keep the whole number part. Okay. And so the height of my building is 165 feet. Ooh, that had a lot of algebra in it, but it was kind of cool though. It was kind of cool. I also love algebra. All right. All right. Objective 3. So letter C. Solve problems involving the bearing of a line. So bearings are used to describe direction and are essential in navigation, surveying, and mapping. By using trigonometric functions, we can determine distances and angles between locations based on a given bearing. Understanding bearings allows us to interpret directional movement in practical settings, such as aviation and maritime navigation. The bearing of a line L or I is the acute angle formed by the north-south line and the line I. The notation to designate the bearing of a line begins with north or south for north and south, followed by the number of degrees in the angle, and ends with east or west, so E or W. Okay. So here in this visual in figure 10, we have 4 different formats for the bearing of a line. In the first one, top left, we have the bearing of B from A is north 40 degrees east. So we always start north or south, so in this case, north. Then we move either east or west. So in this case, we're going east 40 degrees. So from north, we go 40 degrees. Moving to the right, we have a bearing of B from A. So from the point of view of A, we're going north. Then we move 65 degrees west. Bottom left, we have a bearing of B from A is south. So we start south 70 degrees east. So then our angle moves towards the east location. And then for the last one, bottom right, the bearing B from A is south 20 degrees west. So we're going south, then we go 20 degrees west. Okay. So we're now going to look at a couple problems where we're using the bearing of a line. All right, so a boat travels on a course of bearing north 46 degrees, 30 minutes east, or 30 feet east, for a distance of 248 miles. How many miles north and how many miles east has the boat traveled? Okay, well, let's convert first our 46 degrees and 30 minutes to a decimal. Okay, so 46 degrees, 30 minutes would be 46 plus 0.5. Remember 1 minute, 60 minutes is 1 degree. So if I have 30 minutes, I'd have half of a degree. So that would be 0.5. So that equals 46.5. So we know our angle is 46.5. Okay. Since we're going northeast, let's draw our bearing coordinate plane here. So north, south, east, west. Okay. We are going north, and then we have a bearing where our angle, let's draw that better. There we go. Our angle is 46.5 degrees. Okay. And we know the distance traveled is 248 miles. We want to know how many miles east and how many miles west has the boat traveled. So we want to know this distance, which is the distance traveled east, and we want to know this distance, which is the distance traveled north. Okay, so you can say we want to know x and we want to know y. So this would be y and this would be x. All right, if it helps, we can draw our triangle out here. Yep. Let's make it all connect. There we go. 46.5, 248, x, y. There we go. All righty. Okay, so now we need to find x and y. We have our angle measurement for reference. Okay, so we have our hypotenuse and we need to find the opposite and adjacent sides. So we know we'll be using sine and cosine to help us. So the sine of 46.5 is going to be our opposite over our hypotenuse. So x is going to equal 248 times the sine of 46.5. When you plug this into the calculator, you'll get 179.892844. Rounding to 3 significant digits, we'll have 180 miles. X represents the distance traveled east, so this would be 180 miles east. Okay. Now we need to find north, and north is y, the distance traveled north. Y is the adjacent side, so we'll be using the cosine of 46.5, which equals y over 248. So y equals 248 times the cosine of 46.5. When you plug this into your calculator, you should get 170.711948. Rounding to 3 significant digits, we'll get 171 miles north. Okay. All right, so how many miles north and how many miles east has the boat traveled? 180 miles east and 171 miles north. That's pretty cool. Town A is 14 miles due north of Town B. If Town C is 3.5 miles due east of Town B, what is the bearing from Town A to Town C? Okay, so we know we're going to be looking from the point of view of Town A. All right, so let's draw our image. We have Town A. This is Town A. Town A is 14 miles north of Town B. Okay. If Town C is 3.5 miles due east of B, what is the bearing from Town A to C? So what is the bearing from Town A to C? Since we're looking at the point of view from Town A, we're going to apply our north, south, east bearing. North, south, east, west. All right, and we are looking for alpha. We want to know what is the bearing from Town A to C. So this would be the bearing right here. Okay. All right. So we're trying to find alpha, but we know, not alpha, theta. But we know the opposite side, and we know the adjacent side of theta. So opposite and adjacent means we're working with tan. So the tan of theta is going to be 3.5 over 14, opposite over adjacent. So theta be the inverse of tan, 3.5 over 14. When I plug that in my calculator, I get a super long decimal. Make sure it matches to yours. Since the values I've been working with have 2 significant digits, I'm going to round this to 2 significant digits. So theta is 14 degrees. So my bearing is south 14 degrees east. Remember, you always start north-south and then go east or west. Okay, that's cool. I guess this is what they were doing before we had navigation systems. That's pretty cool. All right, let's go through exercise 10. A helicopter is hovering over the desert when it develops mechanical problems and is forced to land. After landing, the pilot radios his position to a pair of radar stations located 27 miles apart along a straight road running north and south. The bearing of the helicopter from one station is north 15 degrees east, and from the other it's south 21 degrees east. How far west is the pilot from the road that connects the 2 radar stations? All right, so for this problem, let's first set up our visual. All right, so let's draw our bearing. So we have our coordinate system here. We have north, south, east, west. The center here is going to be the pilot in the helicopter. Our first station is north 15 degrees east. So north 15 degrees east. So this angle is 15 degrees. So this is station number 1. And then we have south 21 degrees east. So south 21 degrees. Let's make this a little longer, that way we can connect. There we go. This is station number 2. Okay. We also know that the distance between the 2 stations is 27 miles. So the distance between the 2 stations is 27 miles. We want to know how far west is the pilot from the road that connects the 2 stations. Okay, so we are going to assume that the distance west from the station to our north-south axis, aka y-axis, is the same. So we're trying to find these measurements. Okay, so we have 2 different triangles here, and we are going to utilize the information that's given to us to find x. All right, so for our first triangle, we have 15 degrees as our angle perspective. We have to find x, and we know one of the legs is going to be part of 27 miles. So let's just give it the variable yn. So to signify the y, north. For our second triangle, we have our angle perspective of 21 degrees. We're trying to also find x, and the other leg will give it y south for the y displacement south. Okay, so to set up our equations for both triangles where we're able to find x, we will utilize the trig function tan because we know the opposite and adjacent sides. So the tan of 15 will equal x over y sub n, and the tan of 21 will equal x over y sub s. So let's write both equations now in terms of x. So y sub n will equal x over the tan of 15, and y sub s will equal x over the tan of 21. Okay, now I know that y sub n plus y sub s equals 27. So that's the total distance between station 1 and station 2. So that means x over tan of 15 plus x over the tan of 21 equals 27. Okay, so now I can rearrange this problem so that I can get x all by itself. So on the left-hand side, let's factor out x. So that will get me x times 1 over the tan of 15 plus the tan of 21. And now I can divide both sides by the expression within the parentheses. So x equals 27 over 1 over the tan of 15 plus 1 over the tan of 21. Okay. When I enter that into my calculator, I have the value 4.2605971. Okay. But I'm going to round to two significant digits. And so x is going to equal 4.3 miles. Okay, so the helicopter is approximately 4.3 miles west of the road.